Okay, thank you everybody. Thank you so much, Jason. As he said, it's my first keynote. I am equally excited and anxious. I usually give niche talks. People are going to come in the room knowing what to expect. So speaking to a large audience is different for me, but I hope you're going to enjoy the keynote today. We're going to talk about data-oriented design, practical data-oriented design, and I want to start with a photo. This is, when it gets there, this is a photo of Mike Acton giving a keynote at CppCon 2014. That was my first ever conference. And at the time, Mike was at Insomniac Games, and he came on stage and he challenged some of the core beliefs of C++ developers. And this was my personal start of my own data-oriented design journey. I don't know if you recognize this individual, but that is me a long time ago. I don't look like that anymore, right? I look a bit different. But yeah, I was asking Mike a question here, and for me it was a career-changing moment because I hadn't realized at the time that there was another entire way of thinking about code, about software, that was different from OOP. So even if nowadays I don't agree with all the conclusions that were in that keynote, I would still like to thank Mike for opening our eyes, and I would still recommend you to check out his keynote. It's very, very good. Okay, a little bit about myself before we begin. Right now, I am an independent C++ consultant, trainer, and mentor. My business focuses on delivering bespoke C++ training and one-to-one mentorship. I am available for tech training and guest speaking, so if you're interested, feel free to reach out afterwards or check out my website. I spent the last 10 years at Bloomberg. I've been working on high-performance C++ backend development mostly. I worked on around microservice infrastructure team and around market data analytics team. And I've also been doing technical training in terms of both modern C++ and topics such as metaprogramming and multi-threading for Bloomberg Engineering. I am involved in standardization. If you heard of stud function ref, I am partially responsible for that, so you can love me or hate it for it. And that's going to be in C++ 26. You might also know me for the epochs proposals, which I feel like partially lives on with profiles nowadays. So that's also something else you might have heard before. I am quite passionate about games and game development and open source in general. I'm part of the SFML team. I was the person that led the modernization of the library to target C++ 17, so I strongly advise you to check it out. We're going to use it today for our demos, but I also contribute to other libraries, including SDL, and I have 2 commercial games released on Steam, which are also open source, so you can check how the sausage is made. And I also like virtual reality. I contribute to several mods for games like Half-Life 2 and Quake. Last but not least, I am the co-author of this book, Embracing Modern C++ Safely. I wrote this book with my friends and colleagues, John Lakos, Rostislav Pennikov, and Alasdair Meredith. It's a reference of all modern C++ features that covers all the pros and cons in detail. So if you're interested in that, again, feel free to ask me afterwards. But enough about me. Let's take a look at today's goals, today's keynote, and what we're going to do. So the goals for today are, I want you to discover a new mindset. I don't know how many of you here are familiar with data-oriented programming. Can we have a show of hands? Okay, so quite a bit of you and quite a bit of you are unfamiliar with, which is good. So if this might be something new for you, you're going to learn how thinking in a data-first way changes the way you design a system. At the same time, we're going to have a bit of a refresher on how hardware works, especially memory, and how it communicates with the CPU and why that matters for the design of your software. We're going to do this somewhat interactively. We're going to build this little demo together. I'm going to show the demo first, then we're going to gradually build up to it. And we're going to see how changing the way that the data is laid out without actually changing the operations we're doing on the data can really make a difference in performance. At the same time, I don't really want to just focus on the performance aspect of DoD, but I also want to make a point that it can make your code much simpler and much more maintainable than OOP, which might sound counterintuitive, but I'm going to show you some examples where I found that to be true. And also, this is maybe where I feel a bit differently from the rest of the game dev crowd. I think that there still are places where OOP makes sense. We're going to discuss that later. And I think that the use of high-level C++ abstractions can actually help achieve your goals. And there are places where, when used judiciously, can help you get better performance and more maintainability of your code. OK, so I'm just going to dive straight into the demo. I'm going to show you the thing that we're going to implement, and I'm going to give you an idea of what we're going to do. So for this keynote, I chose something which is quite simple and somewhat visually interesting. So we're going to have this demo where we have these rockets flying around. Let me just zoom it in. And every single one of these rockets and smoke particles and fire particles you see on the screen, everything is its own entity, it's simulated, it has its own physical quantities, and you can refer to every particular single thing that you see on the screen through some sort of identity. So to make the requirements a bit more explicit, we want everything to follow laws of physics. So we have basic motion model with position, velocity, and acceleration. We should be able to customize these effects, particles, and emitters of different types with different opacity, scale, and rotation that change over time. Everything is an actor, so if I care about a particular rocket or a particular particle, I should be able to have a handle to it and do something with it. As an example here, every rocket entity has some attached emitters that are kept in sync and spawn the particles. And finally, I want to design this in a way that it is extensible. It should be easy to add new effects, should be easy to add new actors, new particle types, and so on. So it is somewhat of a toy program, but I try to make it a bit more realistic by having this requirement of being able to attach entity to other entities. And I feel like it isolates the performance principles quite well, and the lessons you learn even with this toy program are applicable to real-world code. Now, if I jump here and I open up this menu, you will see that we have some metrics regarding update and draw performance. And if I actually start spawning some new rockets, the rendering is out of sync for some reason, you will see that as the rocket spawns, the frame rate kind of tanks and it doesn't really become playable anymore. I can zoom out as well. I can show you that we have a lot of them. And here you can select the data layout that we're going to use. This is the OOP implementation. But if we switch to something like AOS over here, you will see that we have a dramatically nicer frame rate and it just becomes much more playable. And you can play around with this stuff. You can try other memory layouts and so on. But the point is, we have this demo, we can play around with it. The operations we are doing are the same. What changes is just the memory layout that we use. And as you can see, it makes a dramatic difference. And now we're going to see how that actually works. Cool. So, excuse me. That said, let's just get to work and let's start implementing this. So we're going to start designing this according to OOP principles. So we have our own, let's say, real-world model interpretation of the problem, and we're going to try to transfer that into code. We know that we're going to have multiple entities, so we can start with an entity-based class. We're going to have an emitter class that produces particles. We're going to have a rocket class that flies around and has some emitters associated with it. And we're going to have a particle class. Excuse me. The emitter can either be a smoke emitter or a fire emitter in this case, and the particle in the same way can be a smoke particle or fire particle. What you see in light blue is a base class. What you see in dark blue is a concrete class. Now, I like this. It's a nice and simple hierarchy. If I want to add something new, I can just derive from entity. If I want to add a new kind of emitter or particle, I just derive from those things. It fulfills all requirements, seems easily extensible, so I don't see any particular problem with this. Let's try to implement it and let's see how the code actually looks when we transfer this into C++. So we're going to have a struct entity here. I'm going to use struct just to keep the slides concise, but in reality you would use class and private and public and so on. I'm just going to try to focus on the performance and memory layout aspect of things at this point in time. Because this is going to be a polymorphic base class, we are going to have a virtual destructor. In this case, we can default it. And then we're going to have a virtual update member function that takes the delta time, so the amount of time that passed between frames, and uses that to advance the state of the entity forward. We're also going to have a draw member function, which is virtual. It takes this thing called the render target, which is from the SFML library, and it's just an abstraction that allows you to draw stuff either on a texture or a window. In our case, it's going to be the window of the application, so not very important in this case. Now, because everything needs to follow the laws of physics, we're going to have a bunch of vector2f's here, which are just 2D vectors of floats for position, velocity, and acceleration. And if you want to see how that actually looks in practice, it's just two floats, x and y, with some nice operator overloads that allow you to basically multiply, add, and so on. And again, this is from SFML. It's a nice and convenient abstraction over a 2D vector. And that is pretty much it. If we want to implement the update part of the entity here, we can move the position by the velocity scaled by the delta time, and we can move the velocity by the acceleration scaled by delta time. So very simple physical integration, not the most accurate, but again, we want to focus mostly on the memory layout, not on the accuracy of the simulation. We have a problem though, right? Entities might need to know the state of other entities. They might need to create other entities on demand. So we need some sort of way of making that possible. So one of the things I came up with and I've seen being used in many other places is something like this. The entity knows the world it belongs to. And through that world reference, it can query the state of any other entity, or it can create new entities. It can interact with the state of the world. So we're going to do something like this for our program. And we're also going to have this little Boolean called alive, which is going to be responsible to tell the world, hey, this entity is done. Please get rid of it, recycle the memory, and use that memory for something else. So it's just going to be used to communicate to the world that the entity can be cleaned up. The reason why we use a Boolean is that we want to be able to communicate that through the update member function. There might be some conditions in the update that make the entity eligible for cleanup. Okay, so that's the entity. Just to show you some more code, we have the particle. It's going to have its own scale, opacity, and rotation. They can change over time. So we also have the rate of change as data members over here. We can override the update member function, use what we wrote in the entity. Again, dry principle. We don't repeat ourselves. And then do the same sort of idea of physical integration for scale, opacity, and rotation. The only interesting thing here is that we set the Boolean alive to be true only if the opacity is greater than 0, which basically means our condition for getting rid of particles is when they fade out. Because every single particle is going to eventually fade out in our demo, this is going to be good enough to clean them up when we're done with them. And just to show you what the smoke particle looks like, we just derive from particle. We get everything for free, basically, which is quite nice. And the only thing that we have to change is we want to override the draw member function and specify that we want to use that data to draw something with a smoke texture. And you can imagine this can be done for the fire particle and any other one that you want to add in the future. Okay, the world is probably the most interesting part. We have 3 kinds of entities here already on the screen. We want to store them in such a way that it's convenient for us to work with them. So we're going to do this. We're going to have a std vector of std unique pointer of entity that contains all the entities. So those of you here that are somewhat familiar with data-oriented design might already be thinking, hey, nobody writes code like this. There's going to be an allocation for every entity. It's not going to be very cache-friendly. But trust me, I've seen this in production many, many times. If you look this up on GitHub, even with share pointer, sometimes instead of unique pointer, you have hundreds and hundreds of hits. And you can read stories about this happening in AAA studios. People have successfully shipped very good software that was highly successful with this design. So I'm not saying you cannot do this and you cannot be successful. But if you know that the drawbacks of the design, you also should know that this is actually being done in practice. I just want to know, like, how many of you have written code like this or seen code like this in practice? Okay, so pretty much everybody. This is not toy code. This actually happens. And I also want to say very popular libraries and engines do stuff very similar to this, including the SFML library. So it's something that is used quite all over the place. The update and draw member functions are quite straightforward. We just iterate over all the entities, and we call update and draw. You might see the nice aspect of this. We don't care what update does. We don't care what draw does. We just delegate that to the entity, so it's quite nice. And finally, we're going to do a little bit of cleanup at the end. We have this call to erase if, which is a quite recent function in the cplusplus standard. It takes a container and a predicate, and it efficiently rearranges the items in the container in such a way that they can be removed in constant time. Okay. What else? The emitter, we're going to do something like this. We're going to have a timer that keeps track of how often we want to spawn a particle. We want to have different spawn rates. And then we're going to do something interesting. We're going to define this pure virtual function called spawn particle that is going to be overridden by the actual emitter types. So the update function of the emitter base class will periodically call spawn particle but then it's going to be the derived emitter that actually overrides that and decides what it means to spawn a particle. The smoke emitter will internally allocate a new smoke particle using make unique, and then it will push that back into the world. So you can also see here how we are referring to the world from within the update of an entity in order to affect its state and create new things on the fly. Okay, last thing that I want to show you, which is somewhat interesting, is this. I mentioned that the rocket needs to have some associated emitters. So what we're going to do here is we're going to use raw pointers. We're going to say, okay, I'm the rocket. I need to know what smoke emitter is associated with me and what fire emitter is associated with me. Now, because we have this implicit knowledge that the world is the owner of the entities, and as long as the rocket is alive, those emitters will be alive, using a raw pointer is fine here. We thought about our lifetime, so this works in our model. And this is something that you also commonly see even in large-scale programs. The way you refer between components of the same program is by using pointers. You're relying on the address stability of these objects. The reason why you can do that in this case is because we are allocating them on the heap. So even if the vector gets reallocated with all the entities, even if we move around the world, the address of the emitters is going to be stable. When we create the rocket, we create the emitters and we wire them up. And when we update the rocket, we're going to move them with the rocket. So pretty straightforward. And this is pretty much all the code we need for that demo. So that said, let's see how fast this is. So let's do a little bit of a round of benchmarks. So the machine I'm going to use is not the tablet I'm presenting on. This is my desktop machine. It's fairly beefy. It has an Intel Core i9, which was top-of-the-line processor a few years ago, pretty fast DDR5 RAM, and I compiled using cplusplus with O3. I disabled rendering for these metrics, but I'm also going to talk about rendering here and there, as changing the data layout can also be beneficial for rendering and not just for updates. So with 200,000 entities, we get 2.3 milliseconds, 400K, 6.6, 600K, 12 milliseconds, 800K, 16.6, and 1 million, 21.6 milliseconds. Now, you might think this is just milliseconds. It's fast, right? Who cares? But if you're thinking about targeting real-time applications, the budget in a single frame that you have to reach 60 FPS, which is pretty much the bare minimum for a nice interactive experience, is 16.67 milliseconds. And you can see already at 600K, we're already blowing up most of our budget. And if you think about having to put in rendering on top of that, if you think having to put in more complicated logical algorithms, you don't have a lot of room to work with. At the same time, remember, these are pretty good hardware. So on a mobile device, these would probably be unacceptable. And at the same time, I feel like 60 FPS in 2025 is pretty pathetic, honestly. Even mobile phones nowadays, they have 120 Hertz refresh rate displays. So the bare minimum, I think, for a very nice and interactive experience that feels smooth should be 120, 144 FPS. And if you want to target that particular frame rate, your budget for a single frame is less than 7 milliseconds. So we are pretty limited here. We have almost no budget left, only at 400K particles. And we're talking about C++. We're talking about fast hardware. We should be able to do better than this. Now, we've seen in the demo that changing the memory layout of things speeds up the program significantly. So the problem is not the algorithm. The problem is not the operation that we are doing. The problem is how the data is laid out in memory. And the CPU is actually mostly idle here. It's not doing any work. It's just waiting for that data to arrive and wasting time doing nothing, which is, again, unacceptable if we care about performance. So let's take a detour. I'm going to give you a little bit of a refresher on memory and tell you why it is important that we understand how it works internally to design our software to be efficient and make good use of our CPU. So at a very, very, very high level of abstraction, you can think of the CPU and RAM as being connected by some sort of bus, and they communicate, and everything is fine. If we peel one layer of the onion and we go one step lower, again, at a high level of abstraction, you can think of a CPU as something like this. We have some core where the operations are actually being done, some cache, which is some very small but very fast buffer of memory, and then the communication has to go through a hierarchy. The data that's in RAM first has to go through the cache, and then from the cache to the core, and vice versa. So every operation you need to do has to follow this path through memory. In reality, I have a slide later, we have multiple layers of cache, we have multiple cores, so it's more complicated than this, but the main principle still applies. The memory has to follow this hierarchy and move forward. Now, the cache, you can think of it like this, is a very small but fast collection of rows, and these rows are called cache lines. And this is a very important concept. A cache line is the smallest transferable unit of memory. So even if you care about a single byte, you still have to transfer an entire cache line from the RAM to the CPU, even if you care only about that single byte. At the same time, you can imagine that the RAM is a large collection of cache lines, very, very big, but it's slow. So, for example, if you want to read the data at address 18, it's not in cache, our cache is empty, so we can identify the data being there in RAM, and only if we care about the data at address 18, we still have to take the entire cache line from RAM, which is a cache miss, which means we take the whole row and we copy that into cache. And if you imagine that we don't care about what's adjacent to this data, we don't care about what's next to the D here, then we wasted a lot of time moving data that we don't care about, which is quite unfortunate and uses our cache ineffectively. We can keep doing this. Maybe we want to read some data at address 26. It is not in cache. Again, we identified there in RAM, and we have to take the entire cache line and move it into the cache, which again is a cache miss and quite unfortunate. In the best case scenario, for example, if we want to read the data at address 19, and we identify that it is already in cache, you can see it over here, then in this case, we talk about a cache hit. We don't need to do a round trip towards RAM and back, so we are going to be able to read this data way more effectively. Now, why am I telling you this? What is the impact? How much does it matter if we have to go to RAM, and how much does it matter if we can stay in cache? So I like to explain things visually, so I made like a little animation of a race between L1 cache, which is the fastest but smallest cache in a CPU, and the core, and on the bottom we have the RAM and the CPU. So on the top, we're going to see the best case scenario when our data is already in cache, and in the bottom, we're going to see the worst case scenario where every single time that we need data, we're going to go back to the RAM. Now, this slide is going to be slowed down significantly because we are talking about operations in the orders of nanoseconds, but it's going to be to scale. So keep that in mind. 3, 2, 1, go. So by the time that the data in cache has done multiple round trips, you can see the RAM still, getting there almost at the middle, and we've already done a lot of operations. So this is actually to scale, as I mentioned, this is actually what's happening in your program. So if you have all your data coming from RAM, you're wasting a lot of time just fetching that data. In the worst case scenario, it can be up to 100 times slower. So doing a round trip in RAM compared to L1 cache can be up to 100 times slower on modern CPUs. And just to give you some numbers, the amount of time that the average blink of a human takes is 100 milliseconds. The amount of time that an L1 cache reference takes is 0.5 nanoseconds. So by the time you blink, you can have 200 million L1 cache references. In RAM, it's going to be 100 times less than that. So it's fairly significant. So significant that sometimes the choice of where your data is located is much more important than the algorithm or data structure that you use, which can be pretty surprising, especially if you are deeply into theoretical computer science. Sometimes having an algorithm with worse complexity can perform better on real hardware. Okay, so what have we learned? Very important. The smallest unit of transferable memory is a cache line. So no matter how many bytes you want, you're going to have to take an entire cache line. Generally, this is 64 bytes on modern desktop CPUs. Thankfully, we have a very intuitive way of asking for the cache line size in C++, which is STD hardware destructive interference size. So, you will always remember that, but you can think about 64 bytes. All data must always traverse the memory hierarchy. So if you need something from RAM, it has to go through all the levels of cache and then back if it needs to be flushed back into RAM. which means that the spatial locality of data, so where the data is actually laid out in memory, greatly affects performance. And as I mentioned, sometimes even more so than the choice in algorithm or the choice in data structure. So we can already start thinking about some tips, right? If I have data that is related to each other and I want to access it relatively close in time, after access the first one, I want the second one and the third one and so on, then it is better to store it together in memory, close to each other physically speaking. So preferring flat and contiguous storage leverages the cache better and maximizes the chance that as you are taking those cache lines in, the data that you want is already going to be there because it's part of the same cache line. At the same time, there's also something I didn't mention, which is prefetching. CPUs have this speculative mechanism that basically figures out the pattern in which you're accessing memory. For example, if you're in a loop and you're going forwards or backwards or you're jumping every nth element to a threaded access, the CPU can figure that out and it will already start giving you the cache lines that you might need in the future even before you request them. So also doing very predictable operations can greatly improve the performance of your program. And as I mentioned to you before, I lied to you. The situation is more complicated. So if you want to be a bit more realistic, this is kind of what it looks like in a more modern CPU. You might have an L3 cache shared between multiple cores, which is larger but slower. Each core might have an L2 cache, which is a bit bigger than L1, but a bit slower. And then you might have an L1 cache for data and an L1 cache for instructions. Now, I find this interesting because code is data. When you compile your program into a binary, the actual code you generated has to be loaded into memory. So sometimes, if you optimize your code for size and not for speed, it might actually be faster. And the reason is that it might use the instruction cache better. You might have more of your hot loops fit into the code cache itself. So we're not going to cover that in this talk, but if you go deep into this topic, sometimes the way that the code is aligned also really matters for your performance. Now, this is all I'm going to tell you about hardware and CPUs and memory and so on. I want to refer you to this nice talk from Scott Myers. It's from 2014, but it's still very relevant today. CPU caches and why you care, that goes deep in detail. And also, Jonathan Mueller gave a talk here at CppCon called Cache-Friendly C++, which covers the same topics, and it goes quite in detail as well. So I think if you watch these two talks, you're going to have a very nice understanding, appreciation for modern hardware, and you're going to be able to get a nice intuition of what can be fast or slow. I greatly recommend watching both talks. Just taking a little break. Cool. So given that, why is our implementation slow? And we can actually figure that out quite easily just by looking at the world implementation. We have this entities vector that is a vector of unique pointer, which means every single entity is going to be allocated somewhere in memory, likely not close to other entities, so it's going to be scattered around, which means if we iterate in our update, if we iterate in our draw, and also in our erase-if, in the worst case scenario, every single iteration would be a cache miss. And we have seen how slow it is. It can be 100 times slower than L1 reference. So this is probably the worst case scenario for the CPU. It's just going to stay there waiting for data to arrive. At the same time, we have other sources of overhead. We're using virtual dispatch, we're using vtables and polymorphism. So whenever you access the update or draw member functions, there's going to be a vtable lookup, which had some overhead. Probably not as important as the cache miss, but it's something else that we have to care about. And finally, if you remember the way that we spawn particles, we actually call make unique over here. And erase-if will actually destroy those unique pointers. So we have a frequent churn of dynamic allocation and deallocation. So you can already figure out this is not going to be very efficient. We're doing a lot of extra work, a lot of waiting on memory, and a lot of overhead due to virtual and allocations and deallocations. So my question is, why did we write our code this way? Why did we jump onto the OOP hierarchy and with the virtual interface and so on? And I think this has to do with the object-oriented mindset. So most people's introduction to programming actually is OOP. University, books, whatever, you learn about classes, you learn about inheritance, you learn about the usual shape-based class, which can be circle, rectangle, or the animal-based class, and so on. But also, it's a natural choice. Like, For humans, it aligns quite well with the view of the world. We think in terms of individual objects, individual things, and we have this is-a relationship in our head. It just works well. So this mindset sort of works like this. I identified 4 things that I think are important. We try to model a world of autonomous objects. We think of self-contained agents with their own identities and responsibilities. We have a particle. The particle has its own data. It knows how to update itself. It knows how to draw itself. These entities communicate between each other and with the rest of the program through messages. The main loop, the world, doesn't know what the particle is actually doing. It's just asking, could you please update yourself? Could you please draw yourself? We don't care about the internals. We're just asking those operations to be done. The data is hidden. So we don't care. We don't expose the internals of these classes. We hide them. We encapsulate them. But we expose the behavior. We don't care how the particle gets updated, which might be nice sometimes because it allows us to change the internal representation without changing the behavior. But we're losing information about something really important, about the data layout of our particles. And also, I feel like OOP tends to encourage people to plan for the unknown. So you're going to try to figure out some sort of abstraction or interface that not only works for today's problems, but for any problem you might have in the future. And I chose the word bet here very carefully because in my opinion, it is a bet. It's really hard to predict what kind of requirements you're going to have in the future. And if you get your prediction wrong, getting out of the wrong abstraction sometimes is more expensive than not having done it in the first place. So if you're lucky, you might save some time, but more often than not, it's really hard to predict what might be needed in the future. In contrast to this, if we set this aside, let's see how the data-oriented mindset thinks about the same problems. So we don't want to model a world of autonomous objects. We want to model a world of data transformation. We look at code as a pipeline that transforms data from one state to another. We don't really care about this notion of an object, of identity, of encapsulation. It's just data. We don't have messages. We operate directly on batches of data. So the entity itself is not in control anymore. It's not the individual that matters. We have operations in bulk on the data done from the parent object. The world is going to be responsible for the update and the drawing of all the entities. It is in control. And I'm saying in bulk here because the most common case for this sort of applications is not having a single particle or a single entity. Having many of them is the common case. So why are we designing it with the individual in mind when the actual real common case is having things in bulk? At the same time, we don't want to hide data. Data is the most important thing. We want to make it transparent. We want to lay it out for efficient processing. And we want the behavior to be centralized at a higher level that sees all the data and is able to figure out, oh, this is the best way of actually processing the data that I have. This is also something that I feel like is more subjective, but I have the feeling that this mindset tends to encourage developers to plan for today. You want to design for the problem that you have at hand. You want to prioritize performance and simplicity to solve that problem, and you don't want to solve any problem that you don't have or you might have in the future. And sometimes this might actually pay off. Sometimes it's easier to change your code to adapt to a new problem if you didn't start with the wrong abstraction to begin with. So sometimes this might pay off even for future extensibility. So how do we shift our mindset? I think we have to internalize that no matter what, the only purpose of code is to transform data. The focus should not be on modeling an abstract world of objects that makes sense in our head, but on the data's journey. So we want to get from point A to point B. How do we do that efficiently and in the most simple way? Data is the centerpiece. It's not something that we want to hide. Why would we hide the most important part of your program that actually makes it work efficiently? We actually want to make it visible, understand its shape, its size, and access pattern. And those are the things that are going to drive the design of the application, the operations that we do on the data. Modern computers, even the best supercomputer that you have, they all thrive on simple and predictable work. So as long as you design your program to feed computers along straight runs of contiguous data, you are likely going to get good performance. And finally, this is more of a philosophical thing. You want to design for the machine that you have. You want to be familiar with the platform you're targeting, with the capabilities of your hardware. because an effective solution is not aligned with the metaphor that you have in your head of the problem you're trying to solve, but with the physical reality of the hardware. So this is sort of like the shift that you would have in your mindset if you want to approach data-oriented design instead of OOP. So that said, how can we start optimizing our code to move towards this mindset? Maybe not fully, but moving towards this idea. So for our first optimization pass, we're going to do a few things. We are firstly going to get rid of individual heap allocations, which I think is the main bottleneck of our program. We are going to get rid of inheritance, which is going to flatten our hierarchy. And we are going to decouple the data from the logic. The entity classes will now just be the data, and the logic is going to be one level up. The world is going to be the one that deals with all the behavior so that they can see a full picture of what we have and operate on data in bulk. At the same time, we have a problem, right? Before we had this nice vector of entities where we could store things homogeneously. But now what we're going to do is we're going to have multiple containers, one per type of entities that we want to store. It might seem more cumbersome, but you will see what actually makes sense as we want to process these things differently. They have different properties and different behaviors. Okay, so we're going to have our emitter struct, we're going to have our particle struct, and our rocket struct. They're all going to have their physical quantities. So we have a bit of repetition, but it's minimal. Who cares? The emitter is going to have its own floating point for the timer and the spawn rate, and the particle is going to have the same quantities as before. But now we have a problem, right? Before, we could differentiate between fire and smoke particles because we had this nice hierarchy. So what do we do now? At the moment, I'm going to take the easy way out, and I'm going to do this. I'm going to say we have an enum class called particle type. It's going to be either smoke or fire. And I'm going to store this information in both the emitter and the particle, and depending on that, we will do different things. This is not ideal. We're going to see later how we change this, but so far, this is going to be fine. The other problem that we have is that in the rocket, we need to refer to two emitters. We want them to be linked together. Before, we had this nice property that we could use the address of an emitter. It was stable, and we can use that to communicate between these things. But now, if we are removing heap allocations, there is no guarantee that the address of the emitters will be stable. The vector might reallocate. We might move things around in memory. So what do we do? Usually, there are many solutions, but a common solution for this is using indices. So you're not going to rely on the address stability of the actual object in memory. You're going to rely on the index stability, on the position of this object in the vector it belongs to. You might need to change the vector a little bit. We're going to see how, but it's a common way of dealing with this. Other ways might be using some sort of a hash table where you store the key and then you look up the object. You might have special data structures that are designed with DoD in mind that help you achieve this. But generally speaking, the point I want to make here is that now the relationship is data. It's just a number. So it's not something specific to the hardware anymore, but it's just an index. Okay, so how do we change our world to fit this new design? We're going to have a vector for particles. We're going to have a vector for rockets and an associated addRocket function that ends up doing any wiring that's necessary with the emitters. And then we're going to do this, which I think is quite interesting. We're going to have a std vector of std optional of emitter. The reason why I'm using an optional here is to guarantee index stability. So you can think of this as being slots where an emitter might be in or might not be in. And by looking at the index, we can guarantee that the emitter at index 4 is always going to be the same emitter. If you want to get rid of another emitter and destroy it, we just make the slot empty, but we don't have to shuffle anything in memory so that the index stability is retained. And again, there's other ways you can deal with this, but this is a very simple solution that works for our use case. To go along with this design, we're also going to have an add emitter function that, given an emitter, will put it in the first free slot that is available, and then it will return the index of that slot. And all these things in conjunction, they work together to replace the relationship that was based on address stability by something that is data-driven. We are working with just numbers, indices, and we get the same sort of relationship behavior as before. We're going to have the usual update, draw, and cleanup, so we're going to see how they change. The update function is going to be quite interesting, in my opinion, because now we can operate on all the particles in bulk. We're not telling each particle, please update yourself. We have the full view of the particles, and we just loop over them and perform the operations. And you can already start seeing how the compiler has much more information here to optimize and vectorize and do cool things with this code. For the emitters, we're going to loop over all the optionals. We are going to skip the slots that have nothing inside them. We're going to do our updates, and then we're going to create new particles. Now here, we are actually going to branch on the type of the emitter, and depending on whether it's smoke or fire, we're going to push back something else into the vector. Again, we're going to see an improvement over this later, but so far this is fine. And finally, for our rockets, we move them, that's fine. And the interesting bit is this one. When we want to get the associated emitters, we just look into the emitter vector with the index that was stored in the rocket. We check if that optional is valid. I think it should always be, so maybe this should be an assertion, but I used an if here. And then we are going to set the position of the emitter to be the same position as the rocket with some offset that makes it look a little bit better so that the particles are actually spawning out of the rear of the rocket, right? And we'll do the same for the fire emitter. The last part I want to show you is the add emitter, which is the function responsible for creating a new emitter. What we do is we loop over all the slots. If we find an empty slot that maybe used to have an emitter but now is empty, we can then place our emitter directly there and return that index. So we are reusing an existing slot. If the vector is completely full, then we just then place back. We have a new slot available. This might end up reallocating the memory under the hood, but we don't care because we are not relying on that. We are relying on the indices. Now, this algorithm is linear, but you can imagine that if you want to optimize this, you could have a list of indices that are free, which you keep track of as you create and remove emitters. So you just pop an index whenever you want to create one and use that, and you just push it back whenever you're done. So you can make this constant time quite easily. I just wanted to keep it simple, as the number of emitters in this program is very small compared to particles, and it's not really significant that we have this O of n algorithm over here. Okay, last part, which is the cleanup. We're going to have an erasive for the particles, where we do the same thing. We remove them if they have faded away. We're going to have an erasive for the rockets, where we remove the rockets if they reach the right-hand side of the screen. And at the same time, inside the predicate, we're going to take this opportunity to also destroy the associated emitters. So if we know that we reached the end of the screen, we're also going to reset those optionals that we had in the emitters vector so that those loads can be reused. And then we're going to return true to tell the algorithm, yeah, feel free to get rid of this stuff. Cool. So how does this change our performance? Let's do another round of benchmarks. Same hardware, same program, same conditions. And we have very significant improvement for 200K, even more for 400K. And as you can see, this trend keeps going on. And on average, we have a 70% decrease in update time just by changing the way that we store the data. We haven't changed any operation. We are doing the exact same calculations on the data. We just changed the way that we store it and the way that we process the data. I also am not showing it here, but I also got an 8 times boost in rendering performance, because now that the data is laid out in groups, I can easily take all the particles and send them to the GPU as one thing in bulk, easily take all the rockets and send them at once. So you're going to see over time, if you do this, especially with graphics development, that the data-oriented layout is actually very, very friendly to GPUs. So the more you do this, the more you're going to be able to send data to the GPU more effectively as a side benefit. Okay, so I don't know if this is surprising to anybody, but probably you expected this. But at the beginning of the talk, I also mentioned I want to make this not just about performance, but also about simplicity. So let's see if this is actually true. Let's see if it actually makes things simpler. Now, the first thing I want to show you is, let's say we have a new requirement. For example, we want to keep track of the number of rockets specifically. And this is actually something I tried to do for the demo. I wanted to have a counter for the number of entities in total, but I also wanted to know how many of them are rockets. And I tried, but I couldn't, because in the OOP approach, it is deceptively difficult to do this efficiently. So the first thing I tried in the OOP approach was something like this. I'm going to loop over all the entities. I'm going to use dynamic cast. And if it's a rocket, I'm going to increase the number of rockets. Now, I don't like dynamic cast. I hate it as much as everybody else. but it seems like a good use case for it. It's a statistical metric that I just want to have as a tangential thing, and this is like a edge case. I just want to know how many rockets I have. This worked, but it actually showed up in my profiler. I was losing milliseconds because of the dynamic cast. So it's unacceptable. I would have made this OP solution even slower than it is just to count the number of rockets, which I was surprised about. I thought it would have some overhead, but not very significant. So then I realized, okay, maybe I can do something like this. I can have my entity have a getType virtual member function that returns an entity type, and then I'm going to avoid the amount of overhead that I get from the dynamic cast. But this defeats the purpose, right? I don't want the entity to know which entity it is through an enum. The point of OOP is that I want to think about entities in the abstract sense, and I don't want an entity to tell me what type it is. Otherwise, why am I using OOP in the first place? It didn't seem right to do this. So maybe I thought the rocket itself on construction could inform the world, hey, there's a new rocket in town, and then on destruction, it could tell that I'm going out of scope. But this also didn't feel right. You have more mutation of state hidden within the internals of a derived class, so it's harder to see the flow of the code. And also, I feel like this is an SRP violation. Why is the rocket responsible for metrics? Like, didn't seem right. The world maybe could do this then. Maybe I can have an add rocket function that I can call, and I will create rockets only through that function and will keep track of the rockets. And in the cleanup, I will do some bookkeeping to decrement this. But now I'm having a specialized function for rockets. So again, I want to think about in terms of entities. I want to give the world an entity, not a rocket. It defeats the purpose, right? So I just didn't like this. And there's also more complexity because of the bookkeeping. So I'm not saying this is impossible. You can make this work. It's just overly hard for what I wanted to do. So I gave up in the end. And you've seen in the demo that I just have the number of entities and I'm like, that's the best I can do. So what about the data-oriented approach? That's it. I know how many rockets I have because I'm storing rockets separately. So I just have a simple function called to the size of the vector, and I can get them for free. So I feel like many things, this is just an example, right? And you might think it's artificial. But over time, as I've moved towards data-oriented design, like I'm not saying I'm going to go full data-oriented every single time, I feel like I get these small wins more and more often, so it does make things simpler. So it is also about simplicity. And another example I want to give you is, imagine you are like a new member of the team, and you have to work on this demo. You have to extend the code. You have to understand it. So you're going to go in the code base, and you're going to start doing a little bit of code review. You're going to try to understand how all the moving parts interact, how it works, and what you need to do to change it. So you see the entity here, and you're like, okay, this seems simple. And then you see, oh, but we have a reference to a world and also this extra state for the alive Boolean. And then you start thinking, now every single entity might end up doing something that changes the state of other entities. And to know that, I have to cross-reference all the files in the code base to see what's happening. You have to jump around the source code to get the full picture. At the same time, this doesn't really sit right with me. This is really annoying. Because we are putting the draw member function in the virtual hierarchy inheritance API thingy, we have very tight coupling with the rendering system. So if we want to change from SFML to SDL or another library, we're not going to do that because we're going to have to change 20 classes, and they're very tightly coupled together, which is quite unfortunate. At the same time, if you look at the world, you remember, yeah, this seems simple on surface, but actually it's hiding anything. This update could end up destroying entities, could end up creating new entities. So how do I know what's happening? I have to look at every single entity. So I think in practice, this makes it hard to understand the full state of the system. You need to keep into your head all the possible derived classes that are there and what they can do at any point in time. And yeah, if you remember, this ends up affecting the outside world, so I think you get my point. For the data-oriented design, I find it nice that the entities themselves are just data. Like, there is a clear separation between logic and data, and there's nothing hidden there. It's completely decoupled, and what you see is what you get. Like, there's no special side effect in the constructor of any member or anything like that. It's just plain data, which is simple. At the same time, if I look at the world, I can immediately see what things are in the world. I know I'm going to have emitters, particles and rockets, and nothing else. There's nothing that could be added in from a runtime, from some other derived class or something like that. You can easily see all the types. So the data is not hidden. And at the same time, in the single update function, I know exactly every mutation, every operation that's happening. I can see the stage-based approach where everything is changed on a pipeline basis. All the logic is there, and I can see the relationships between all the entities in the same place. So I know if a rocket is going to affect an emitter, if an emitter is going to spawn a particle, everything is going to start in this update function. Now, for the coupling issue, you still have some coupling here with the rendering system. So you still have that thing there, the render target appearing in the world, but it's much looser, right? If I want to change rendering system, I don't have to change n classes that end up dealing with drawing. I can just change it in one place, do the right transformations, and it's going to be a bit easier to adapt this to some other system. So I feel like this is much easier for somebody, especially new to the program, to get an idea of what's going on. And I feel like this also opens up new opportunities. So I'm going to get there. I'm going to start by adding this new requirement. Let's say that we want to be able to serialize the data. Now, this could be useful for many things, saving and loading, networking, and so on. So how do we do it in the object-oriented approach? You could do something like this. You could have your entity being extended with a serialize and deserialize virtual member function. The serialize take an outstream, the deserialize take an istream. So probably the second one shouldn't be const, but slideware. This might work, but I feel like the coupling is too tight. I am locked into a specific format because at this point, I need to decide whether it's going to be XML, JSON, binary, or whatever. And also, I'm one of those people that cares about compilation times. I have a few talks about the subject here and there. And by doing this, I'm going to make every user of entity virally include IO streams, which is pretty beefy header and is going to slow down compilation. I don't want that. I want these things to be separated. I want the serialization module to be the only place where I include whatever dependency I need. So one of the common answers to these kind of problems in OOP is design patterns. We can use the visitor pattern. We can have a nice visitor base class that deals with all the derived types. Entity can accept visitor in this virtual member function. And then I can create a serialization visitor, deserialization visitor, maybe one for JSON, one for XML, and so on. Nice and decoupled until you realize I'm listing all the types again. So I'm losing that benefit of OOP. I have to think about every possible derived types in the same place. We lose that individual responsibility principle, which is quite nice, to be honest. We revert back to having to put all of this in the same place. We also have more overhead. It's actually double dispatch. We're going to have 2 virtual calls every time you call this function. Now, for serialization, might not be significant, but if you use this pattern for other things, it might actually be significant. And also, you have to keep everything in sync with all other visitors. And one thing that I don't like is that something that should conceptually be a function parameter, DO stream should only be available as a function parameter whenever I want to serialize or deserialize, now becomes state. It becomes a member of the class. But it doesn't have to persist. I only need it for the duration of the serialization function call. So why do I have to store it there? And even worse, then you realize this, right? You have your rocket, and in your rocket, you're using pointers. So what do? It's not impossible. Again, you can make this work, but you have to figure out a mapping from pointer to something that can be serialized, and then you would have to figure out a reverse mapping when you deserialize it. You can make this work, but does it have to be so complicated? I'm just trying to serialize some state, and I have to do all this stuff. Okay, in the DoD approach, it's just a single function. You have a function called serialize. You take your world by const reference, it's just reading, and then your string, and then internally, you do your serialization. Of course, you could split this into separate functions. You could have a serialize for rocket, particles, and emitters. But the point is, you can isolate this in its own translation unit. Any expensive dependency can be isolated to TU, so you don't have to worry about compilation times. And it's quite simple. Everything is there, you see it, and you don't have to jump around in your source code. So I think it's a nice win even in this case. At the beginning, I mentioned opportunities. So why am I talking about opportunities? Because once you do this, you realize that the entire state of the program is just data. It's just bytes that are meaningful. There is no reliance on pointers or addresses. So saving and loading, which is something that people dread implementing, becomes trivial. You literally just serialize and deserialize in a row, and you're done. This leads to better testability, debuggability, and tooling. If you have an interesting edge case that you want to test, you just save the state and you write a unit test to repeat that. I know of gaming companies that do this. For example, the people behind Factorio, they store interesting edge cases with their game, and then they have this unit test suite where they load the state and they run it and check that the result is exactly what you expect. Debuggability, you have a weird bug that it's hard to reproduce, you save the state and you replay it as many times as you want. You can check the state at will. Tooling, now everything is data. You can write a nice UI, so during runtime, you can change relationships, you can change the values of your classes. It becomes a little kind of like in-game editor for your own application. So you get a lot of benefits out of this. Networking becomes easier. You can send a snapshot of the entire state over the wire, and the other player or user will get the exact same view. And then anything on top of that can be a delta that's been sent on top of the last snapshot. So having everything just being data helps a lot and creates new opportunities for things that are useful. Okay, what about multi-threading? I'm going to go a bit quicker. I don't have that much time left, but in the OOP approach, let's say we would just want to multi-thread the particles. We care about the particles, the bottleneck. We don't care about other things. How do we make it multi-threaded? Well, it's a bit difficult, right? This could do anything, could create new particles, could be an update on something that is not a particle. So it's not really easy. I would say it's not really parallelizable because also we have rights to linked entities from the update of other things. So you cannot just trivially say, I'm going to take the loop and split it into chunks. That's going to be data race hell. Yeah, you could make this work. Maybe you could filter all the particles in advance and then store them in a separate vector and then do that in chunks. But the overhead of doing that will likely defeat the purpose of multi-threading in the first place. With DoD, you see your update as a bulk operation in your update function in the world. And now this is probably the most trivially parallelizable loop you've ever seen. You can do this in horizontal chunks, vertical chunks. You could even get away with just OpenMP and you just stick a Pragma OpenMP parallelized there and it's going to do it for you. So I think this is like the easiest thing to parallelize. Again, this is a simple example, but I want to show you that something that is conceptually simple becomes complicated if you apply principles that are meant to help you but actually end up hindering you. So my point is that data-oriented design architectures provide many side benefits. It's not just performance, but you're going to get better simplicity, better flexibility out of it. But can we go even further? Can we make this even more optimized, even faster? So we're going to do a small optimization pass here just to get rid of branching. What we're going to do is we're going to try to avoid branching in hot loops. And the way we do this is by grouping the data beforehand. We're also going to take an opportunity at this point in time to try and reduce the size of common types. One thing that you'll learn very quickly is that small is fast. The more things can fit in cache, the better performance you will have. So if you have types that are unnecessarily big, trying to reduce the size of types or the padding that you have inside your types will end up having better performance in the long run. But we're going to stop here. No other major changes. We're going to stick to this layout, which is called array of structures. Later, we're going to migrate to SOA, structural arrays, and we're going to see how that actually affects the performance. So this is what we had. We had this particle type. What we're going to do now is we're going to get rid of that. So we're not going to have that enum anymore. We're not going to have those extra fields. And I'm going to show you that the world is going to be responsible for grouping the particles depending on their type. We make that branching implicit, if you will. At the same time, I realized we're never going to have more than a few thousands emitters. So why are we using a size T? Size T is 64 bits, pretty big, but we don't need that. So I can change this to a uint16. It is more limited. You have to be a bit more careful with these values now. But because I know the nature of my program, I'm going to save some space for the rocket. Maybe by doing so, I'm going to be able to load more rockets into the same cache line as I'm iterating over them. Now, this is not going to be very impactful because rockets are not a bottleneck here. I just want to show you the idea, the principle. If you have something which is in a hot loop and you can figure out, let's say, constraints about the data of the fields of the objects, changing the data types, reducing padding, reducing size, can actually improve performance significantly in some use cases. Okay, what else? So if we look at the world here, we have to do a change, right? We cannot just store particles anymore because you don't have a way of knowing which kind of particles they are. So we're going to have more containers. And this is another common transformation in DoD. You end up having a lot of containers that implicitly provide information about some properties of those objects. So the first container tells you everything in here is a smoke particle. The second one tells you everything in here is a fire particle. And we do the same for the emitters, and we tweak the API a little bit. And this is how we actually represent the various types. Of course, if you have a lot of types, then you can think about metaprogramming, generating these things at compile time, or using even a runtime generation mechanism if you're loading these things on demand. But for now, because we only have 2 types, it's fine to hard code. In the update member function, we are going to use little lambda here as a local function to avoid repetition. Again, C++ abstractions, modern features, and data-oriented design can coexist, in my opinion. They can be synergetic. And I'm going to avoid repetition here and just have 2 loops, one for smoke particles and one for fire particles. For the emitter, it's the same thing, and I'm going to use a little higher order function here. So this lambda is going to take another lambda called fspawn, which tells the emitter what kind of particles should be spawned. And then when I actually call this, I'm going to specify as a callback that the smoke emitters should spawn smoke particles and the fire emitters should spawn fire particles. Again, I feel like it's a little bit of abstraction, a little bit of modern feature usage, but it's enough to avoid repetition and still keep the code very linear and simple without hiding what's happening under the scenes. So I think this is a reasonable amount of abstraction. That is it. Once we do this, we can do a little bit more benchmarking, and we're going to see that it's not that big. There is a consistent improvement of around 5.73% in terms of decreasing update time, which is small, but we'll take it. And as I mentioned, this particular optimization here wasn't very impactful because most of the bottleneck in our program is updating the particles themselves, while the branching was not the hot loop. But depending on your workloads, doing something like this might give you a much better performance increase. Not pictured here is also, after doing this change, I got a 12% drawing improvement, like rendering performance improvement. And the reason is that now the data is, again, laid out more nicely for the GPU. I know that all the particles that are fire particles are going to be in one container, and they all use the same texture. So I can just send that to the GPU, and the GPU is going to be happy. And you can do the same with the smoke particles. So DoD really aligns very well with what the GPU wants. And it's good to keep in mind if you're going to do graphics development or if you're going to use GPUs to accelerate your programs. OK. Last thing that we're going to do is we're going to change data layout. So you always probably hear this idea of SOA structure of arrays. Is that actually going to be beneficial? Is it actually going to make a big difference? So why don't we just try it and see how that performs? The idea behind SOA is quite simple. Instead of having a single struct that represents an individual particle, you don't do that anymore. You have a struct that represents a collection of particles, a struct of arrays. So each individual field of your particle is not going to be an individual field, but it's going to be a collection of fields. So you lose the explicit object, the explicit entity. Now a vertical slice over all these vectors, just like a table, becomes your entity. So we're going to have this particle SOA struct that contains positions, velocities, accelerations, and so on. And the implicit invariant here is that all vectors are going to have the same size, and they're going to be growing and shrinking in sync. So all of this stuff should be in sync. Visually speaking, looks like this. The AOS layout, every index is a complete object with all its fields. The SOA layout as I mentioned, is like a table. Every index contains a vertical slice which represents, conceptually speaking, a particle, but you don't really have that in your code anymore. So if you want to do a little bit of a comparison, the AOS layout has explicit entities. Every object is a real entity in the code, while the SOA as implicit entity is a conceptual slice across the arrays. AOS might suffer from internal padding. If you have alignment requirements for your fields, the compiler might end up adding some extra bytes in between them that are still going to take space in the cache. So you might be wasting cache space because of padding. With SOA, because every container contains only a single type, unless you're using some weird type that has some alignment requirements as a decoration, then every single byte is going to be useful. There's not going to be any waste of cache space. This is very important. If you only care about a single field, for example, we only care about the position of particles. We just want to find all the particles that are out of bounds, right? With AOS, it doesn't matter. You still have to load things you don't need because position is close in proximity in memory to velocity, acceleration, other things. So even if you only care about the position of the fourth particle, you might get some data from particle 3 at the end loaded in cache, and maybe the velocity and acceleration loaded in cache as well. So if you need a subset of fields, you're going to waste a lot of space accessing other things. With SOA, we have what I like to call the surgical field loading. If you only get what you need. If you only care about positions, you're not going to pollute your cache by putting in things that are not positions, which is quite nice. AOS is naturally resistant to vectorization. The data is scattered. SIMD instructions like when the data is, homogeneously close to each other. It is not impossible. We're going to see that it actually happens, but it makes it harder and a bit more expensive. SOA is ideal for vectorization. It's exactly the way that SIMD instructions like the data to be in. It makes it trivial for the compiler to perform auto-vectorization, assuming that you're doing operations on the data, which are quite simple and straightforward. And it's not on the slide, but again, I would also say SOA also is very nice for GPUs. GPUs like that layout a lot compared to AOS. So yeah, let's implement this. Let's see how it actually behaves. One thing I'm going to do before implementation is just have a little helper function here because I hate repeating things 9 times. So I'm going to have this function called for all vectors. It takes some callback f and applies that function f on top of all the vectors at once. You can imagine that if you want to resize or reserve all the vectors at once, instead of copy-pasting the same dot resize 9 times, we can just call this function once and provide the right operation. Just a little helper that avoids repetition of 9 times the same code. That's going to be our particle SOA. Then we take our world, we change our vectors of particles to be particle SOAs. We could have done this for for rockets as well, or emitters. Not very significant. The bottleneck is particles, so I'm not going to bother. And in the update member function, again, I'm going to use a little lambda here that updates a specific particle SOA. I'm going to get the number of particles. Here I'm just using positions, but you could use any vector. Again, the implicit invariant is that they're all the same. And if you've seen Barry's excellent talk on Monday, he showed you how to use reflection to create SOA automatically, and it stored just a single size and capacity to avoid that waste. I just wanted to keep it a bit simpler, but I recommend seeing that talk if you are interested in that. And I'm just going to loop over all the particles via index, and I'm going to perform these operations. So now you might be thinking, does it make sense to have a single loop? Is it better to have 5 loops, and each one individually just loads the thing that it needs? I've tried it. In all scenarios, having a fused loop was faster. So again, depends on your cache size, platform-specific, let's say, constraints and requirements. In my situation, having a single fused loop was always faster. The last thing that I want to show you is the emitter update, because this is not nice. You're going to end up doing this. So whenever you want to spawn, for example, a smoke particle, this is what it looks like. You're going to have 9 calls to pushback, where everybody is going to be a single field. And honestly, I cannot defend this. It's horrible, but that's what we get. Yeah, so it's pretty much the same. I'm not gonna bother seeing the other things. The cleanup is the other interesting part because you're gonna find some friction with standard library algorithms. They are not designed with SOA in mind. So what I did here is I defined this has negative opacity helper predicate, which doesn't just take the index, but also the SOA it belongs to, and it tells me whether that nth particle in that SOA has faded away. And then I wrote my own erasive for SOA. And I'm going to pass in my particle SOAs and my predicate to remove those particles. Now, what does that look like? Just to show you, to give you the idea, it's kind of like a partition algorithm. I'm going to start from the left and the right. I'm going to skip over all the particles that don't need to be removed. And then I'm going to move everything that needs to be removed towards the right-hand side by using the for each vector to perform the swaps simultaneously on all 9 vectors at once. And then at the very end, I'm going to resize all the vectors at once. And you can probably see the value of that small helper function here. Otherwise, you would have had to use 9 calls to resize and so on, which is not great and very easy to make a mistake. So how much does it matter? How much is the improvement here? And it's quite big, actually. We have around 32% decrease in update time. And at the same time, I promised I would tell you about rendering performance 2 times faster. And the reason why it's 2 times faster is because I can simply map the fields to GPU buffers, and I can just send everything contiguously at once, which is very, very efficient for the GPU. But if you think about it, why are we getting this nice big boost of performance? This is probably the worst case scenario for SOA. I mentioned before, SOA is very nice when you want to get subset of fields, like if you only care about position, if you only care about scale. But here, for every single particle, we're using all the fields. So it should be, comparable to AOS. We're still loading everything in cache. Why are we getting this huge boost even though we are not leveraging some of the nice properties of SOA? And of course, to figure this out, I went to the assembly and I was taking a look at the AOS versus SOA. You can see that in both cases, you get SIMD instruction. We get a fuse, multiply, add for the integration steps, which is probably the best thing you can do here with floating points to perform that, integration of velocity and so on. But for AOS, you have a few extra operations here. You have something called gather and scatter. So what gather does is it takes data that is laid out in a strided way, and it loads the addresses of that data into a single SIMD register so that everything is contiguous. And then the scatter does the opposite. It takes that data and then it scatters it back to the place where it came from. So there is some overhead when applying SIMD due to the fact that the data is not laid out contiguously. It first needs to be shuffled around a bit for SIMD to be applied on top of it, and then it needs to be put back where it came from. So this is probably the biggest overhead that we get here is because of vectorization. There might be other factors here that affect the performance difference. Because the particle data in AOS is all contiguous per particle, you might have some cases where the same particle lies on the boundary between 2 cache lines. So to read one particle, you need 2 cache lines. Prefetcher might have a bit of a harder time with threaded access. I don't know, just a theory. And this is actually something that might be very impactful because when we're doing the gather and scatter, we also need to use some registers to store those values after them being gathered. Then you might have a bit of extra register pressure. You might have fewer registers you can use for meaningful operations as you're doing the SIMD stuff in here. So this is how I explain the performance difference. If you have any other insightful ideas, you can let me know afterwards. What about simplicity? Did we sacrifice simplicity? And my answer is, with this current design, absolutely yes. I don't want to write 9 pushbacks. It's not simple. It's ugly. So the problem is that C++ has no real native support for the SOA layout. The language and the standard library are all built all around AOS. I would have lied to use std erasive, but I could not have done that. Maybe you can write some sort of proxy iterator that when you dereference and stuff like that, it just scatters through all the vectors. Don't want to do that. It doesn't sound simple. So it would have been painful. We've seen how some functional programming patterns help. Just simple things like a local lambda or passing a function to another function can help reduce repetition significantly with very small effort, so that's good. But can we do any better? And I think, it's time to reflect on that. So we have this, right? I like this. Simple, understandable. I don't like this. This is a manual transformation that I don't really want to do. I would like to work with a particle as it is on the left-hand side and get all the benefits of SOA. So it would be cool if I had this magical SOA type that is a template. I can give it a particle, and internally it builds up that structure that we mentioned before, all the vectors for every single field. Would be really cool. And then if I had this, I could call pushback, and I could provide all my fields as a particle, and internally the SOA wrapper would scatter them to their targets. It would be so much nicer to write that compared to 9 pushback calls. Maybe I could have a with all interface that I could use to loop over the data. This would expose all the fields in order as if they were an actual object, but they are still going to be loaded from separate vectors. So it gives me that nice AOS-like way of thinking, but the layout is still SOA. But more importantly, maybe I could have something like this. I could say, look, I only care about the scale and the scale change, the rate in which the particle changes its size. So please give me those 2 fields only, load only that memory, and then execute this lambda over here. So maybe I could have this with function. I specify the fields that I want with some pointers to members, and then I provide the lambda expression to actually work on those fields. Would be cool, right? This is valid 17. You don't need to wait until cplusplus 26. You don't need reflection to do this. You can do this in cplusplus 17, and I've done it using Boost PFR, which is a very nice library, very underutilized, which allows you to do reflection on aggregates. There are limitations. It's not full-fledged reflection. I'm still extremely excited and happy that we're getting reflection in 26, but I think that people underestimate how much you can do even before that. cplusplus 17 gives you tools that you can abuse to get reflection for aggregates. And this kind of transformation is something you can actually implement yourself, which is quite nice. And I will link you the code at the very end. At the same time, can we do better? If we had cplusplus 26 reflection, we could do this. You don't have to specify those things twice. You don't have to say that you want the address of the scale field and the address of the scale change. The reflection system could just look at the names of the parameters and the types of the parameters you specify in your lambda, and from those names, it could figure out which fields to load from the SOA. I don't know how I feel about this. I think it's just, the initial impact that having names of things being so significant is a bit scary, but it is the future that we're going to have. Reflection is going to enable APIs and interfaces that heavily rely on names and things like that, so you better get used to it. Now, I'm not going to implement this because Barry, again, had a fantastic talk on Monday, really good in its own regards, that I strongly recommend you go and see, that deals with this problem specifically. It shows you how to use reflection in 26 to transform an AOS data layout into SOA automatically. I've shown you that you can do that even in 17, but with 26 reflection, I think it's way more straightforward, allows you to do more things, and I'm excited to see what people come up with in the future. So go check out this talk, and you're going to get all the information you want about reflection. Cool. Almost done. Just a few more things. SOA is not always the answer. I think there is a misconception, and people think data-oriented design means SOA. No, really. Data-oriented design means something more important than that. It means that you design your architecture with a major focus on the layout of your data. The access pattern that you're going to use to operate on your data chooses the layout, not the other way around. So you have to ask yourself questions. Which fields are frequently accessed together? Maybe those things should be together in memory. Are there any cold fields that I might use only once in a while? Maybe you can store them separately from the rest of the fields for the same object because they're going to just waste cache space. What is the SIMD lane size on this platform? Your architectural choices might depend on what you're targeting. You're targeting a PlayStation, you're targeting a laptop, might be different, right? But this is where probably I would disagree with the rest of the game dev community. I like abstractions. I like being able to say SOA of particle. And if I have that, and if I have maybe AOSOA, which is like a hybrid layout that does the same thing. I can experiment. I can see which one is better on this platform. And just by switching my SOA to AOS or to some other template that does something similar, just by doing that compile time switch, I can keep the rest of the code exactly the same and see how the memory layout affects the performance. I like being able to do that. So switching between layouts at compile time will be something you can do, and 26 will make it easier. With reflection, you can implement any sort of transformation that you want that allows you to experiment and try out new layouts and see how it changes your performance. And also, DoD is not always the answer. I don't hate OOP. I think that OOP is problematic when it's used at the wrong granularity. If you use OOP at a higher level, coarser granularity, I think is a great tool. If you have an OOP particle manager with a nice API that does encapsulation, gives you private and public access, has nice environments and so on, and internally you use DoD for speed, by all means do that. And if you do so, you can also swap strategies at runtime. You can have a particle manager virtual interface that then you implement for a AOS implementation, SOA implementation, and so on. And because the virtual calls are going to be just a few compared to a few million, it doesn't matter. It's nice to have that possibility and that sort of flexibility thanks to the OOP principles. So OOP is not bad. It's just it's sometimes used at the wrong level of granularity. Also, if you're working in teams and with other people, having clear boundaries and the SRP, single responsibility principle, can boost collaboration. If you have large teams with novice developers, having invariants and access control can help people understand how to modify the code. Also, I've worked in places where we can agree on an interface beforehand, and then we implement that interface in parallel for two different things, and then we merge it later on. Having that sort of like layer of abstraction is really useful for collaboration. You can use polymorphism for plugin systems, but what I recommend is a hybrid approach. OOP is the shell, and DoD is the engine. So if you manage to find a nice, reasonable way of combining those at the right levels of granularity, you're going to get the best of both worlds. Almost done. Some final takeaways. Design for performance from the start. If it is a requirement, it must be an architectural priority. It's not premature optimization. If speed is a requirement, like you need to target a certain frame rate or something like that, you must take account of it in your design. After you do that, then you can profile and see what the bottlenecks are in that particular design. But don't think about the premature optimization. It's something important for the success of your program. Flatten and shrink your data. Prefer vector of t to vector unit pointer of t. You're going to avoid all that extra indirection and have stuff more contiguous. Minimize the size of structs using hot loops. And steer away from polymorphism and inheritance trees for things at a small granularity. For high granularity stuff, might be a good idea to use them, depends on your use case. Group data by usage. Instead of having a single container and a lot of flags and booleans that you branch upon, use more containers. Make those flags and booleans implicit by pre-arranging your data. It's not just good for performance, but also helps you see everything that you have already laid out. It helps with simplicity and understanding of your code. And if you have bulk processing, which might benefit from SOA, consider it, but don't think that DoD always means SOA. As I mentioned before, it's a mindset, it's a way of thinking. Data drives design. Target the machine. It's a spectrum, not dogma. Embrace modern C++, it helps. And pragmatism always wins. So I just want to leave you with this. Think data first. Your code will be faster and simpler. And thank you so much. I will take questions.
Okay, I have a question.
Yes.
So you asked the first question in my talk, and I appreciated that. I think this talk was perfect. You've actually done what allocators can do by hand in the sense that you've laid everything out using vectors. Vectors don't have the same problem as other kinds of containers because as you delete them and put things back, because there's no internal part to it, you don't get the kind of diffusion you would had you designed in a composite world. If you were not designing at this level, but in an intermediate level, can you see that allocators could recover much of the loss? Could you talk about that?
Yes, so it's a good question. I consider talking about allocators for this talk. I wanted to keep it a bit simpler and a bit more philosophical in a sense. But I do think that if you end up in a situation where a pragmatic way of recovering performance out of a design that has been OOP and it's really hard to change because of change friction and stuff like that, allocators can help you, definitely. I would be surprised if I didn't get a huge speed up by applying an allocator for those entities that I had before. So it would be something interesting to try out, would be something interesting to benchmark, but I do suspect allocators are a good, pragmatic intermediate solution to this problem. Sorry.
There. I think an object-oriented programmer would say you've lost some of the relationship between some of those objects. Like there was a very sort of clear relationship between say the rocket and the emitter that you sort of lose in that sort of data layout. So I see there's benefits, but what would you say to that?
So I would say by looking specifically at the data itself, I can see the point. One comment I have to make is that just use a plain integer for the index, but you could use handles, you could use strong type defs that have more semantic meaning in terms of the relationship they express. On the other hand, I feel like that relationship becomes much more visible when you are operating on the data. If you look at the update loop, you actually see what is being done with that emitter, with that rocket. You don't only see that there is a relationship, but you actually see what the relationship is for. So I think you gain more than you lose in that particular aspect. Sorry, yeah. I have to get used to this.
Hi, thank you for the talk. I really like this kind of design. I was wondering how would you compare the testability in between an OOP design and a DoD design? Is it easier?
What kind of stability, sorry?
The testability.
Testability, yeah. So I think from DoD point of view, you get some nice benefits. For example, as I mentioned before, because your program is just data, right? You can literally store an interesting test case as data, load it, and try different things on that. I mentioned there are gaming companies that do this with complicated scenarios that they want to test out. They just store a save file and they load it and so on. With OOP, that becomes a bit harder because you don't have that easy serialization aspect that I mentioned before. OOP might be nicer in some aspects. For example, mocking is one of the places that I was thinking of, or dependency injection. So I think as long as you apply the OOP at the right level, like the higher level components, you should use OOP, right? I'm not saying never use OOP. I think it's just using it at the wrong level causes problems. So if you are doing some business logic where you have a database, abstraction, that could definitely be an OOP abstraction. Then you could mock that into your own system. But then the processing you might be doing on the data you get from the database, if you represent every row as a heap allocation, that's where you lose the performance benefit. So I think they both have their own strengths and cons. And if you apply them at the right level, you can use them also in testing. Let's put it this way. Make sense? Yeah.
Thanks. Really evocative and tight example. Are there any tools or techniques to find where I have that memory pressure and where I should be thinking about applying these types of transformations?
Yeah, so I had quite a good experience with the Vittorio profiler from Intel. It was able to tell me what the bottlenecks were, how often my CPU was idle, and if I was using the cache properly. I'm sure other profilers can do similar stuff. In the past, I've used, I think it was part of the Valgrind suite, there is a call grind tool as well that does something similar. So definitely profilers can identify how much you're using. Even perf, tells you how much percentage is being spent on actual work, on cache misses and stuff like that. So that might be an initial step. Then something like Vittorio, which has been more precise, might be something that I would recommend. Yeah.
Thank you for the nice talk. For the structure of arrays approach, what are your experiences with views? For example, if you have a particle view that just has references on the data members, does this impact performance, or can the optimizer optimize this away?
So my experience is limited. I've tried some stuff out with ranges and things like that. One of the things I've noticed is that, for example, when using ranges, the zip view and things like that, without optimizations enabled, you get very significant overhead and also quite significant compile time overhead, which I wasn't a fan of. So I think that if you are able to always compile with full optimizations and you can ensure that the compiler is inlining those things, it might be as efficient as a handwritten version. I find that a more functional approach where you just provide the callback leads to having less pressure on the optimizer and the code being efficient, even if you are not able to optimize, for example, for debugging, easiness, and stuff like that. So I would like to see a world where I can recommend, hey, use this stuff all the time, but there are practical concerns with debug performance and compile times that makes me a bit wary of doing that. Maybe with reflection, if you unrolled a very flat view that doesn't have many layers of abstraction templates, then it might be significantly less problematic even when you don't have optimization and stuff like that. So again, I would think that C++26 will enable this to be much more effective with reflection. Make sense?
Thanks.
Hey, thank you for the talk. It was really illuminating.
Thank you.
The question I have is, I kind of got a feeling that having a batch kind of processing is really important to reap all the benefits that a DoD architecture would give you. What are your thoughts on non-batch accesses, like if it's random access or you're processing only few entities that are spread out and not aligned with the caches?
Yeah, so in general, again, it depends on your requirements, right? As I mentioned before, there have been very successful games and applications that don't care about any of this, right? They just allocate all over the place. It works. They don't have to reach high frame rates and stuff like that, so they can get away with it. If you are in a situation where your data is naturally graph-shaped or something like that, it becomes a bit trickier to do this, right? Because the pattern that you're accessing the data in is not as intuitive, as simple as we see in the demo. But there are layouts, for example, if you know that you're going to do a level order transfer over a tree or a depth first transfer, you can still lay out the data in a flat array in such a way that as you're performing the transfer, the leaves the nodes that you're going to access after the parent that you're currently at are going to come right after. So again, my recommendation would be, if performance is a requirement and you want to make sure that you use your architecture efficiently, think about the access pattern and think about potentially not perfectly aligning the data in such a way that it is following the access pattern, but at least maximizes the chance that it's going to get in cache as you're loading it. Does that make sense?
Hi, nice talk. I just had a question on when you flattened all the data, you actually duplicated the data versus just deriving from the struct and just using the leaf struct. Is there a downside to do that? Because then you have no duplication, and seems like the memory layout would be identical.
Yes. So I consider doing this. There is no drawback in performance. You are correct in saying that the memory address is going to be identical, so it's going to be performing the same way. It's a bit of a choice in how explicit you want to be. Like if I look at this struct, I want to be able to see, hey, this thing has exactly these fields. If you derive from that, you also have to look one layer up when you're reading the code. It's not a big deal, right? But it is one extra step you have to take. The other thing I'm concerned about is once you get that inheritance, even if it's not virtual, if it's not polymorphic, somebody eventually is going to start relying on that. Somebody's going to see, okay, I can use an entity reference here to refer to something. And then if you want to change perhaps the way that you're storing physical information in the meter, you realize, hey, I don't actually need the velocity in the meter. It's always going to be synced to the rocket. Then you won't be able to do that. So it creates a bit of extra coupling in that situation. So
the upside is if you add one, you just add it to one place, right?
Yes, yes. So I think there's pros and cons, definitely. Yeah. Something you have to consider. I don't think it's a bad idea to do so. I think there's, again, some pros and cons to both approaches. If the repetition is significant, I would very likely do this. But for just 3 fields, small, right?
It also still would work with the struct of array, right? Because you end up.
Yeah, you get the same layout anyway. Yeah. So inheritance, which is non-polymorphic inheritance, is a good tool to reduce repetition for sure. Mm-hmm. I would apply the same logic that I would do for functions. Small piece of code, just a few times, maybe not worth it. Mm-hmm. Big piece of code, used a lot of times, definitely extract it. That's what I think.
Thank you.
You're welcome.
Hello, thanks for the talk. I'm imagining your example as more of an engine than just a standalone thing. Say a user wants to add an update where the rockets move around, change color, rotate, whatever. How do you bake that in to where you are still only passing the data over once per frame per update?
So are you referring particularly to changing the data layout to support more requirements, or is it about the rendering? I'm not sure I get the question.
More requirement, I guess. Yeah, more requirements. Yeah.
Yeah, so I think in the end, like if the requirements change, you're gonna have to change the code in a way or another, right? With OOP, if you had a nice abstraction that managed to predict correctly what you needed to do, you might need to do less work to apply those things, but it depends on your initial abstraction. In this case, I don't see a major problem, right? If you want those requirements to be hard-coded in the binary, like you say, okay, version 2 now is gonna support differently colored rockets. Then you might start adding a color field to the rocket, see if that is good enough, or you could consider splitting rockets by groups, like we've seen before, having a container per color or something like that. If you want something more dynamic, like saying users can dynamically at runtime change properties of things, then I think that's where we get into scripting languages. So I would probably provide the basis of the entities in the code base. I would add support for all the major sort of like fields like color, size, opacity, and so on. And then I would have a scripting engine that runs after the update that would end up allowing the user to do stuff like that. So I think that's probably what I would go for if you need full flexibility. Make sense?
Thank you.
First off, great presentation. Love the way you presented all that material. It's very easy to take in, very informative. So one of the things I take a lot of flack for in my merge requests is using callbacks, quite a bit. And the way that I use them, though, is because I prefer the machine to know what task it has to do, as opposed to going through like a function pointer and then having to determine if this is here, do this. I prefer to skip all that and say either do your task or do these two things first. The classic example being, let's say you enable logging on your service, and then the function pointer approach would be execute this function, check if the logging queue exists, because it's a pointer to it. If it doesn't exist, then move on. If it does exist, log first, then do your task. Whereas I prefer to say, hey, on program startup, I want you to take in a Lambda that just captures all these things and then sets the callback to either log or not log off the jump. So that way, whenever you hit your callback section, you just go, okay, do my task and not check if this, then do task. Is there like really a problem with doing it in that way when it comes to thinking of the speed of your code and like avoiding Lambda captures and whatnot? Because I know Lambda captures tend to get a bit of a bad rep if they're done poorly, especially with lifetime issues. But for performance issues, is that really much of a concern these days compared to everything else?
So it's an interesting question. I think I would have to get a bit more context on the application performance requirements, stuff like that. So when you use the lambda, is it like stored as a std function? Like do you have the polymorphism? Yeah, so if std function has some overhead associated with invocation, right? Because you have like the virtual dispatch and all the stuff. So if you're calling a std function in a very hot loop, might be a problem, right? But if you're calling it in a few places, might not be a problem. It depends on whether you're in a hot place or not in your code base. I don't know about your use case. I would have to see that, but it doesn't sound unreasonable. If you are in a situation where you can afford the overhead std function, it solves the problem cleanly, I think it's fine. You've seen in my demo, I did use a lot of callbacks also with auto to avoid that overhead. I tend to prefer callbacks that are, for lack of a better word, local, like in the sense you define the callback, but the place where you invoke it is close. Like you can see where that is. I've worked in code bases where callbacks can call each other from very different places, and it becomes pretty hard to figure out where that comes from. So I think that's, again, there's a little bit of art involved. There's not a hard rule. Depending on the requirement you need of performance, std function might make sense or not. Depending on your architecture, how far away the callback is in terms of like cognitive overhead, might be a good idea to use it, or might be a good idea to use another technique. So if you want to discuss this further, I'd be happy to later on. Maybe you can show me some more context, and maybe I can give you some better advice.
Yeah, good answer. Thank you.
You're welcome. Cool. I think we are done if there are no more questions. Thank you so much for coming. Cheers.